5:45 in the morning on the 4th of February 1947, Portsmouth dockyard. The temperature had not risen above freezing in 11 consecutive days. Lieutenant Commander David Ashworth stood on the frost-covered dock and looked at HMS Tireless, a submarine, a warship designed to hide beneath the surface of the ocean and destroy enemy vessels, and now, in the pre-dawn darkness of a British winter that had turned catastrophic, a power station. Extension cables ran from the submarine's diesel generator housings across the dock, up through improvised junction boxes and into the grid servicing Portsmouth civilian district. Somewhere across the water, a hospital's heating system was running, a bakery was operating, a telephone exchange was staying alive. All of it powered by a Royal Navy submarine that had no business being a utility company. This was Operation Blackcurrant, and the fact that it existed at all told you everything you needed to know about what February 1947 was doing to Britain. To understand how Britain ended up connecting submarines to its national grid, you have to understand what the winter of 1947 actually was. It did not start dramatically. January was cold, uncomfortable, grey, the kind of winter that post-war Britain had learned to endure without complaint. Fuel was rationed. Coal was scarce. The country was running on austerity economics and the residual determination of a people who had survived 5 years of German bombing. A cold January was not going to break anyone. Then February arrived. On the 23rd of January, temperatures dropped below freezing across the entire British Isles simultaneously. Snowfall began in the north and moved south with unusual speed. By the 4th of February there was deep snow covering every county in England, every major road artery, and most critically every railway line connecting the coalfields of Yorkshire, Nottinghamshire, and South Wales to the power stations that kept the country running. That last detail was the catastrophic one. Britain in 1947 ran on coal, not partially, not mostly, almost entirely. Coal heated homes, coal fired the boilers at power stations, coal smelted steel, coal dried grain, coal kept hospitals warm and factories operating, and coal moved from the pit heads to where it was needed almost exclusively by rail. When the railways stopped, Britain stopped, not gradually. Not in the way that a machine winds down over time. The shutdown was shockingly fast. Within 72 hours of the snowfall reaching its peak, 750,000 railway wagons were stranded in sidings and on open track across the country. 750,000. The number sounds abstract until you work out what it means in practice. It meant the coal that was sitting in those wagons was not moving. It was sitting in fields and cutting and yards across England, Wales and Scotland, perfectly accessible and perfectly useless, buried under snow and unreachable by locomotives that could not get traction on iced rails. Power stations began to shut down on the 6th of February, not all at once. One by one, as stockpiles ran out, boilers went cold, turbines stopped turning. The grid began to fail in sections. Yorkshire first, then the Midlands, then parts of the South. Emmanuel Shinwell, the Minister of Fuel and Power, announced emergency restrictions on the 9th of February. Industry would receive electricity for only 5 hours each day. Domestic consumers would receive none between 9 in the morning and 12 noon, and none again between 2 in the afternoon and 4. Violation was punishable by fine. 5 million workers were laid off within the week, not because their industries had failed, because there was no electricity to run the machines. The British public, still carrying the psychological weight of the war that had ended less than 2 years earlier, absorbed this information with the specific exhausted fury of people who felt they had already paid enough. The Admiralty had been watching the situation develop with concern that was both humanitarian and institutional. The Royal Navy maintained substantial assets at coastal installations: Portsmouth, Plymouth, Devonport, Chatham. These were not small facilities. They employed thousands of civilian workers. They contained machine shops, dry docks, supply warehouses, medical facilities. They also sat adjacent to civilian communities that were now losing power. The proposal that became Operation Blackcurrant emerged from an engineering assessment conducted in the first week of February. The question was straightforward. What assets did the Navy have that generated electrical power independently of the national grid? The answer was diesel generators. Destroyers had them. Cruisers had them. But the vessels with the highest ratio of generating capacity to dockside accessibility were submarines. A submarine in harbour runs its diesel engines on the surface to charge its batteries. Those same engines can be connected to external loads. The electrical output of a submarine's diesel generators was not enormous by industrial standards, but in a town where the hospital and the telephone exchange and the water pumping station had gone dark, it was not nothing. It was, in fact, the difference between functional and non-functional for a carefully selected set of critical services. The operational planning took 48 hours. It was not complicated work, but it required coordination between naval engineering officers, civilian power authority representatives, and the port authorities at each location. The physical connection between a submarine's electrical system and a shore-based grid was not a trivial undertaking. Voltage matching, frequency synchronization, load balancing. These were problems that required qualified engineers solving them in sequence, in the cold, with improvised equipment, because the standard connectors and junction housings designed for this kind of work did not exist. Nobody had planned for submarines to be power stations. The connection hardware had to be fabricated. At Portsmouth, the work was led by Warrant Officer Thomas Belcher, a Fleet Air Arm electrical specialist who had spent the war maintaining the power systems aboard aircraft carriers. Belcher worked continuously for 31 hours to design and install the junction system connecting HMS Tireless, and subsequently, was HMS Truncheon to the Portsmouth shore grid. He used components sourced from the dockyard's own maintenance stores, from a requisitioned electrical supplier in the town centre, and from a destroyer undergoing refit whose generator systems were temporarily cannibalised. On the night of the 9th of February, the connection went live. The diesel generators on a submarine produce a sound that carries. It is not the refined background hum of a shore-based power station. It is a mechanical, rhythmic, purposeful noise, deep, continuous, the kind of sound that tells you something is working. Residents near Portsmouth Dockyard reported hearing it through the walls of their houses on the evening of the 9th. Some of them did not know what it meant initially. Then the lights came on in the hospital on Queen Street. Then the telephone exchange announced it had restored service. Then a bakery 2 streets from the dockyard produced the first bread it had baked in 4 days. The generators ran continuously, 24 hours a day. The submarine crews rotated through watch duties to monitor the systems, manage fuel consumption, and respond to fluctuations in load demand. The fuel supply was itself a logistical problem. Diesel arrived by road, which had partially cleared in tanker lorries that pulled up to the dockyard gate on a schedule coordinated by the naval supply officer. At Plymouth, HMS Subtle came alongside on the 12th of February. At Devonport, HMS Sanguine connected to the shore grid on the 14th. The operation expanded to include 3 additional vessels at Chatham by the 17th. At each location, the procedure was variations on what Belcher had developed at Portsmouth. Local engineering officers adapted his junction system design to the specific electrical infrastructure of each port. At some locations, the connection point was a dedicated shore supply terminal originally designed for submarine battery charging, which simplified the work considerably. At others, the connection required more improvisation. The power delivered was selective by necessity. A submarine's generators could not power an entire town. The output was directed to the highest priority services at each location: hospital heating and surgical lighting, telephone exchanges, water pumping stations, and the port facilities themselves, which needed to remain operational to receive supplies arriving by sea. Coal could not travel by rail, and some of it was now travelling by ship instead. While the submarines ran their generators, the effort to clear the railways was proceeding by brute force. 100,000 men were working the lines. British Army soldiers, Polish veterans of the Second World War who had not returned to a Poland now occupied by Soviet-backed government. German prisoners of war who had not yet been repatriated, still present in Britain almost 2 years after the armistice. They worked with shovels, hand tools. Some locations had mechanical equipment, but the deep snow and the frozen ground defeated most of it. The work was manual, continuous, and conducted in temperatures that remained below freezing day after day. They were clearing 750,000 wagons. The scale of the task meant that the railways began functioning again not as a system but in fragments. A line would clear between 2 points. Coal would move across that section, then the next section would still be blocked. Progress was measured in miles of cleared track and counted in wagons released. The first coal trains began moving in quantity in the 3rd week of February. By that point, the The worst of the crisis had already occurred. Several power stations that had shut down had suffered boiler damage from the rapid cooling and could not return to service immediately. Factories that had been idle for 2 weeks faced the problem of restarting machinery that had been cold for that entire period. Agricultural losses were severe. The submarines kept running. At Portsmouth, the final connection was maintained until the 28th of February, when the local power authority confirmed that grid supply had been sufficiently restored. Lieutenant Commander Ashworth was present when Belcher's junction system was disconnected. He later noted that the generators of HMS Tireless and HMS Truncheon had operated continuously for 19 days without a single significant malfunction. That detail is worth sitting with. 2 submarines designed for combat operations in the North Atlantic and the Pacific, repurposed in 48 hours to serve as coastal power utilities, ran without interruption for 19 days in conditions no one had planned for. The engineering held, the crews held, the improvised connection systems held. It worked. The full scale of what Operation Blackcurrant achieved is difficult to state with precision because the counterfactual is impossible to measure. What happens to a hospital that loses power for 19 consecutive days in February? What happens to water supply systems that cannot pump? What happens to the telephone infrastructure that coordinates emergency response? The answer is that things fail in sequence. Not dramatically, not all at once, but in the specific grinding way that infrastructure failure propagates through dependent systems. Operation Blackcurrant interrupted that sequence at the coastal locations where it was deployed. Beyond the immediate utility of the power, the operation demonstrated something that the Admiralty and the civilian government took different lessons from. For the Admiralty, it was a validation of the adaptability of naval assets and naval personnel. Sailors trained for combat had, without significant retraining, operated their vessels as power plants for nearly 3 weeks. The technical improvisation had been rapid and effective. The institutional response to the emergency had been organised in 48 hours. For the civilian government, the lesson was more uncomfortable. The fact that submarines had been needed at all was a consequence of a coal distribution system that had no redundancy, a railway network with no contingency for severe weather, and a national fuel policy that had left stockpiles at power stations critically low before the cold weather arrived. Emmanuel Shinwell's tenure at the Ministry of Fuel and Power did not survive the year. Britain's winter of 1947 ended the way bad winters always end, slowly, incompletely, with the cold retreating in stages rather than withdrawing in a single decisive moment. March brought thaw. The thaw brought flooding, because the ground could not absorb meltwater that had been accumulating as snow for weeks. The floods damaged roads and railway embankments that had only just been cleared. The country had come through it. Just. The post-crisis assessment produced a series of changes to fuel storage requirements, railway contingency planning, and emergency power protocols. Some of these changes were implemented quickly, others took years. The British winter of 1947 was severe enough to produce political consequences, but not quite severe enough to produce the infrastructure investment that would have made the next severe winter less damaging. That winter would come eventually. They always do. But in Portsmouth and Plymouth and Devonport and Chatham, in February of 1947, in the depth of the worst winter Britain had experienced in the 20th century, Royal Navy submarines sat alongside civilian docks and ran their engines and kept the lights on. Not because anyone had planned for it, because someone looked at what was available, worked out what was possible and made it work. The generators ran, the hospitals stayed warm, the bread got baked, 19 days, 0 casualties, 0 major malfunctions. It worked.